Okay, welcome to this tutorial. My name is Kwast and I'm a junior lecturer at University of Gondar, Institute of Technology. This tutorial is prepared for 5th year hydraulic and water resource engineering students on the course GIS and remote sensing, and specifically for the topic stream and catchment delineation. Before proceeding to the main section, it is important to acknowledge the reference that we are going to use in this tutorial. We are going to use a book by Vander and Menke that is with the title QGIS for Hydrological Applications, Recipes for Catchment Hydrology and Water Management. Dr. Vander is a lecturer at IHE Delft. Then the first thing that before proceeding to the stream and catchment delineation is defining what a catchment or a watershed mean. Basically, this catchment or watershed is a confusing term because of the usage of the terms in American and British accent, but the acceptable one were the one with both accents that you will be using. Agree will be drainage basin. We will define catchment or watershed as a drainage basin. It is an extent of an area of land where the surface water from rain, melting snow, or ice converges to a single point at a lower elevation, usually the exit of a basin where the waters will join another water body. That means a river with a high order, or a lake, reservoir, estuary, wetland, sea, or an ocean. So the basic or the generic procedure that we are going to follow when we are going to do this catchment delineation is the following. First, we have to download the DEM tiles of the study area. Then we have to, at this point, we have to be sure that the study area must be covered, or the catchment we want to drive should be covered completely. Then if the study area is covered with multiple DEMs, then the DEMs should be mosaiced and the tiles should create a single raster DEM layer. The DEM tiles, or the DEM that we downloaded from the open source, these data source websites, may have a different projection or coordinate system. So we have to reproject it to the coordinate system of the project area. Then, in the case when the merged tiles or the mosaic tiles are larger than the expected or the proposed study area, we have to subset the DEM, or we have to clip it. We call this one subsetting the DEM. Then the next step will be the interpolation of voids. When the pixels with no data value exists in the DEM, we need to do the interpolation. Then the next thing will be filling the sinks, making this hydrologically correct DEM. In other words, if we have a stream flow data that is already known, we can also burn into a stream network if it is available. On this tutorial, we are not going to see this interpolation and burning into a stream network. Then the next thing will be calculating the flow direction, where all flows are flowing from higher elevation to lower elevation. Then we will grab the streams, then define the specific outlet point or the outlet of the drainage basin. Then finally we will drive the catchment. Then we will convert the dataset to a model format. The dataset can be used for hydrological modeling or hydraulic modeling. So we have to prepare the dataset in the way that the model needs. Then I will proceed to the downloading of the DEM tiles. We have to navigate to a website called www, this Earth Explorer, usgs.gov. You can find SRTM DEM tiles with 90 by 90 meter or 30 by 30 meter resolutions. This is an open source an open source portal for US United States Geological Survey, and you can have multiple options to download these DEM tiles. You can use the map, navigate using the mouse, or add coordinates like I currently add 3 coordinates, which is where the study area is located. The study area is located, in my case, around the northern Ethiopia, northwestern Ethiopia, on the upstream side of the Lake Tana, which is the area which most rivers are found, like Menke River, like the bigger Angereb River, the Shinta River, the Tekeze River. You can mention some of the rivers which will form the Menke River, and the others, the main Angereb River, the bigger Angereb River, which is a tributary of Tekeze River, which is also the main tributary of the great Nile River. So I will add my last coordinate here. My last coordinate will be is a latitude of 12, then 03, then 00. Now I already added the coordinates, the last coordinate, and hopefully it will create a rectangular data. Then I will choose data sets on this option. Then I will choose here the digital elevation. I will choose there should be choose the digital elevation, then the SRTM, then I will choose the SRTM ARC second global dataset. Then I will click the results, and as you can see, I found 4 tiles of DEMs. I can see how the total area of the project area covered. I can see how these tiles covered the total project area by clicking the footprint. I can show the footprint here, the footprint of one tile, the footprint of the second tile, the footprint of the third tile, and the footprint of the fourth tile. As you can see, these four tiles are combined and gave the project area's location, the digital elevation model of the project area locations. So I'm going to need mosaicing on this case to cover this whole area. Then I will click submit standing request. Then it will automatically download everything from here. I can say download here. It will give me a format, and I will say download the GOT format, and I will also download this one, the GOT format. I will download all 4 of them, and I will add it to my QGIS. I already finished the downloading process, so the next thing to do will be adding the DEM tiles in the QGIS environment. I will start the QGIS here. QGIS, I'm going to use QGIS desktop, which is 3.8, or the version that's called Pandibar. Then I'm going to add these DEM files. I'll open data source manager, then I will select the raster dataset. As you remember, these GeoTIFF files are image digital elevation models. We will talk about the digital elevation models. Before working on digital elevation models, it is also important to talk about these digital elevation models. I'll select where I put these digital elevation models. I'll select all of them, all the 4 of them, and I'll open, then add it. And as you can see, these DEM tags are present here. These are 4 DEM tags, as you can see, downloaded with the elevation values ranging from 400 up to 3,500. This is the elevation variation with these digital elevation models. Then we have to see what a digital elevation model means by now. Basically, these digital elevation models are digital terrain models, which are quantitative models of a part of Earth's surface in digital form. This can also be called this digital surface model. That when the DTM includes all the natural or human-made features. When it is everything is included, we can call this digital surface model. Then how can we acquire these digital elevation models? Most of the time we got it from these satellites. Satellites, but you can also acquire it from ground surveying. You can develop digital elevation model from ground surveying. You can use a digital GPS or a differential GPS measurements, or you can use a stereo photogrammetry, or you can also digitize contour lines and create a digital elevation model. Then what will be the use of these DEMs? The use of these DEMs may be determining the catchment area, delineating the drainage network. You can do 3D simulations, you can calculate the slope, identify geological structures. You can also create or generate contour maps from these DEMs. So the next step that we are going to do will be following our procedure that I introduced in the beginning. The next will be if there are DEM tiles, a number of DEM tiles, we have to create one raster layer by mosaicing these DEM tiles. Then we have to do it using raster. You have to navigate to raster, then miscellaneous, then build virtual raster. Then I have to select all the elements here, and I have to say okay. Then I have to untick place each input file into separate band, because I'm not doing remote sensing analysis. So I'm going to uncheck this one. So I'm going to run it. Okay. The virtual layer is created, and all the 4 tiles are merged to be one virtual layer on one virtual raster layer. The basic thing that you are going to do will be, before doing any analysis, will be saving your project. It is an important thing. I have to save it here. This is Ethiopian modified, and I will say it here, Ethiopian modified. I'll call it just like this. I'll save my project just like this. It's saved. And also when I'm doing every analysis, I have to save it, because I'm going to reproject this one. I will keep the virtual layer just like this, but in the coming all process, I will save everything, because I don't want to lose any file. The next step to do will be reprojecting this virtual layer into an Ethiopian projection system. The Ethiopian projection system is conventionally in QGIS environment. We use WGS 84, UTM 37 North. So we will navigate to spatialreference.org and search for this WGS 84 zone 37 North to find out the EPSG code. I will click the search button, and it will show me the following EPSG codes, and the one that is perfectly matching is the last one, this one, EPSG 32637. I will take that number and go to my QGIS environment and change the projection. To do the projection, I have to navigate through raster, then miscellaneous, projections, then wrap or reproject. Then on the input layer, I will choose this virtual layer. On the target coordinate system or coordinate reference system, I will try to search the one that I found, 32637. 32637, and it will show me exactly this one. If you navigate and check it again, if I enlarge this box over here, it clearly can be shown that Ethiopia falls with this UTM zone. Then the other thing will be setting the resampling method to use. I will choose the default one, the nearest neighbor. Then the no data value for output points, I'll put here -9999. Then the output file resolution, I will need 30 by 30 meter name. Then I will save to file. Then I will navigate to my folder where I saved all the other files. I will call it Reprojected DEM. Then I'll say save. Then I will run it. Okay, now we finished the reprojection process. Now we don't actually need the virtual layer no more, because we are going to work with the new one that is already reprojected. I'll remove this legend. Then the next thing will be changing the on-fly projection, on the project. It is currently on-fly projection, so I will change it to the projection system of the project area or Ethiopia. I click on EPSG. As you can see from the corner, the coordinate reference system is EPSG 4326. So I will change this one. I'll click here, and it will show me just like this. And I will search now also 32637. 32637, and I'll choose this one, and you can clearly see that Ethiopia falls in this UTM location, Universal Transverse Mercator location. Then I will say apply, and I will say OK. As you can see now, the EPSG code of this project is changed to 32637. Now there is no on-fly projection, and it's now a good time to save my project. I will save it. Okay, after saving the project, following our generic procedure for delineating the catchments, the next one will be subsetting a DEM. Subsetting a DEM means minimizing the extents. That means I will have a boundary file. I will create a boundary file from Google Earth environment, and I will minimize the area of extent of system so that it will not take longer time for analysis, and I will have a more specific project area. So I put these place marks to create my boundaries on the Google Earth before drawing any polygon on the Google Earth, so that I will have accurate outbound boundary. So I will add here. There are tools here. I will say add, then I will say a polygon. Then when this dialog comes up, I will say area of extent. Then I will come here and draw the polygon. As you can see, you can draw it simply just like this. I already made many points. I'd rather do it again. It's better to do it again. I'll select, or you can use this polygon, and I'll say area of extend, and I will come here. I will have one point here, the other point here, the other point here, and the other point here. Then I have the extent of area already, and I'll say OK. Then I will save this one. I will right click area of extent and save this place as, and I'll have two formats, KMZ format and KML format. I will use this KML format, and I will navigate to my folder where all my files are found, and I will say area of extent KML, and I will save it here. Then I will come back to my QGIS environment, and I will add a vector layer. I will navigate to my folder, this one, and Ethiopia modified. Then I will add this area of extent KML, and I will add it, and I will close it. As you can see, it's not visible. As you can see, my area of extent is already added on the DEM file, the reprojected DEM file. Then I will change this one to a shape file so that I can extract this one by mask and subset the DEM. Then I will right click and export, then save future as. Then I will say S3 shape file, and I will navigate to the folder where I saved everything in essence, the one I'm currently working on. Then I will say bound. This is a boundary. Then I'll save it, and the coordinate reference system should be 32,637, because it should be similar with the other layers, because I don't need any on-fly projections anymore. Then I'll say OK. Then as you can see, the bound is already here, so I don't need this area of extent file. I will remove it. Then I will save my project. Then the next thing would be extracting by mask of this DEM to have a smaller size DEM, so that my analysis will not take that much. Then the next thing that I am going to do will be clipping the raster by a mask layer. I will go to raster, then I will go to extraction, then I will say clip raster by mask layer. Then I will choose the input layer, this reprojected one. then I'll choose this bound one. Then the coordinates, the target coordinate system, you can also set it here. This will be 32, 6, 37. I'll choose this one and I'll say OK. And assigning the specified node data value to the output commands. It will be the default. Then I will check the match extent of the clip raster to extent of the mask layer. It will be checked. And the X resolution to the output points and the Y resolution to output points. It's also optional. I will leave it like the default value. Then I'll save this one. And I will call it the DEM subset. This one is the subsetted DEM. Then I will run it. Then if I close this one and I unchecked the boundary and the reprojected, I will only have the clipped or the subsetted DEM already that is minimized to the area where my specific project is. Okay guys, after clipping by mask, we did already the subsetting process, subsetting the DEM. Let's check whether we are following the right procedure or not. We will navigate to our folder where I put all the teaching materials. Here I will navigate to this one and I will open lecture 6 and see whether I'm following the proper way of the generic way of delineating this catchment. Let me check it. Then this one is the subsetting process. We already here. We already downloaded the DEM tiles. We already modeled the tiles. We project to the coordinate reference system of the project area, which in our case is the northwestern Ethiopia, with the EPSG code of 32637, or in the naming of the UTM or the Universal Transverse Mercator Coordinate Projection. It is UTM 37 North, and we are already at this point. Subsetting them, we already clipped the mosaic virtual layer into the specific project's area location. Then if there is a void in our DEM due to the data processing or during downloading the dataset, we have to interpolate and fill the voids. In our case, we already found DEM tile that is 30 by 30 meter resolution, and I don't think we need this kind of process, interpolation of the voids. But to talk about the definition, voids are pixels with no data in your DEM as a result of acquisition procedure. Most of the time we discuss about the acquisition procedure of the DEMs. It can be from the differential GPS or any other satellites or drones or aerial photogrammetry. Then voids can be interpolated using the values of the surrounding cells. We will use the surrounding cells values to interpolate the no data values or fill the voids. Then the next procedure is filling the sinks or removing the spikes. Filling the sinks is an important procedure that we need. When we are creating a DEM, it can result in artificial pits in the landscape. A pit is a set of one or more cells which has no downstream cells around it, and pits are removed using the fill sinks function in GIS software. In this case, we are using the QGIS desktop application. Then, if the landscape contains real sinks, for example, the real sinks can be the lakes or reservoirs or another depressions. This needs to be added after removing removing the pits. Then these pits or sinks can be removed by or cutting through or filling up. We can fill up to the the elevation higher than the sink, or we can cut the higher elevation and produce the filtering, or by using cutting saw. We can use these two procedures. Or another procedure can be burning the stream networks. If you have a stream network or a river network available for your project area, you can just burn it to the actual dam and create the exact Thermian arrangement for the proper flow direction. That means the algorithm will follow the river network. The algorithm or the generic procedure that we develop for stream or catchment and delineation will follow this burning in the stream network. So the next thing will be how we are going to do this filtering or removing of the spike. We already have this clip mask or the subset dam. Then the easiest way to do will be using the Saga algorithm, the fill sinks. I will type in here the fill sinks here. Fill sinks. There are various fill sinks algorithms here from the GRASS provider and from the Saga provider. As you see, we are going to use the one under the Saga provider, terrain analysis, hydrology. There are three fill sinks that's developed by Wang and Liu, and the other one fill sinks XXL, that's also developed by Wang and Liu. For the sake of this exercise, we are going to use the algorithm that is better in performance, which is the fill sinks developed by this Wang and Liu under Saga. Then we will select the dam subset here. The minimum slope, I will leave it to the default, and the field dam I will save it to file, and it will be I will call it a dam fill. Then the other thing will be the dam fill. Then the other thing would be I don't need to have this flow direction to calculate the flow direction in the watershed basins. At this moment, I will calculate it after doing the standard order, or after I order the streams, or after ordering the streams in their orders. We call that standard order. That will be the next step. But for now, I will only do the filling process. I will simply run the algorithm and see the process. It will take a while to run this fill sync, so you have to wait patiently. Now, as you see, the algorithm fill sinks has finished processing. So we are going to style the field dam. I'm going to select the field dam layer, and click on the styling panel, or you can press alternatively F7 to do the styling. Now I'm going to select here the single band gray in the color rendering. I will select the single band pseudo color, and as you can see, when I am selecting anything on my layer styling, it is updating the layer automatically, as you can see, because I already checked the live update here, the box here. If you uncheck the live update here, every change you made will appear after you click the apply button. So on my case, I do not prefer to press apply every time. So I did check this live update. Then I already choose this single band pseudo color. Then I'm going to right click on this color ramp. Then I'll say create a new color ramp, and I will select the catalog CPT city. Then I'll say OK. Then when I say OK, the CPT city color ramp will display colors based on different parameters. There are different colors. If you see, you can find the blues, the greens, the grays, the QGIS color ramps when you have a precipitation data, when you have a temperature data, and when you have a topography, when you are doing also topography or bathymetry. Then you can also have the transparency option. In my case, I'm going to select the topography. Then I'm going to select elevation because it is a digital elevation model. Then I will select it just like this, and this will give us more intuitive colors in the DEM where we can clearly distinguish the higher and the lower areas. Now we are going to improve the visualization further. The next thing to do will be right-clicking on the I will click apply, and I will right-click on the field DEM and say duplicate this layer, and as you can see, there is a field DEM copy. Then the next thing will be unchecking the DEM field or the field DEM and renaming the field DEM copy into the hillshed. I'll do that, renaming the layer, and I will call it hill shed. Okay, then I'll check this one. I will check these layers. Then I will go to the layer styling option for the hillshed, and I'll change the color rendering to hillshed format. As you can see, you can clearly see that the real topography of the area is visible now. If you change the direction of the wheel here, this is the altitude, or the azimuthal direction. You can clearly see the actual elevation of the hills in the area, and also the depressions clearly, as you can see when I am rotating the wheel of the azimuthal direction. It is changing with respect to the location of the azimuth. For example, I will leave it here on the northwestern area because my project area is located there. Then this one is to visualize the ups and downs, or the higher elevations and the hills and the gorges of the area. You can determine also, or you can possibly guess where the location of the stream flows, or the direction of the stream flow before calculating the flow direction. So the next thing will be I will check in the field DEM, and I will increase the transparency. I will go to the layer styling, and the next thing to do will be the layer rendering. the blending mode should be multiply. When I say multiply, as you can see, the visibility of the higher and the lower elevation is more visible, or the transparency of the actual layer or the field them is better now. So we did improve the visualization of our layer. So the next step will be according to our generic procedure after filling the sinks or removing the spikes and making it better in terms of visualization. The next step will be calculating the flow direction map. So what do we mean by the flow direction map? The flow direction map shows the direction of the rivers and the river network, starting from the tributaries or starting point up to the outlet point. Then we can use different types of algorithms to calculate these flow directions. The first type of algorithm is the D8 algorithm, and the second one is the DM for the D infinity algorithm. The D8 algorithm uses 8 discrete directions to calculate the flow direction. These 8 discrete directions are 0, 45, 90, 135, 180, 225, 270, and 315 degrees to the steepest cells downwards, while the D infinity algorithm uses the continuous directions. In our case, we are going to use the D8 algorithm, which uses 8 discrete positions or degrees. Then, because I jumped the burning stream network step in here, because we don't have this river network of a specific project area, so we will jump into this calculating this flow direction. The next step will be that. But before calculating the flow direction of the map, we have to order the streams. That means we have to put a threshold that which streams will appear on our delineated watershed map. We have to decide a threshold, which one will be the tributaries and which one will be the mainstream, will be decided by calculating the structural orders. Then the higher the order will be, the bigger the stream. If it has a higher order, that means the river will be bigger. For example, if I have stream orders 4, 3, 2, 1, that means the 1 will be the smallest, the smallest or the last tributary, and the second will be a medium one, and the third will be the third will have a tributaries which has order of 2, and a stream with order of 4 will have tributaries with structural order 3. This is the way to order the streams in a way that it shows us the flow accumulation. It will lead us to the flow accumulation and calculating of the drainage basins. So we will try to order our streams and define our threshold for this specific project. Now we are going to use the structural ordering of the streams, so that I will type in here in the search box. So here, and from the Saga provider, I will have terrain analysis and channels. I will select this one structural order. Then I will select the field DEM. It's already selected. Then I will save the file as I will save to file. Then I will say it and I would say save. Then I'll run it. document and see how the layer will be generated. It will also take some time. We have to wait for that patiently. Then after after the algorithm has finished, we are going to produce a map with a stellar order. Then in the stellar order, the layer can be a Boolean, discrete, or continuous raster. But in this case, where the stellar order that we are going to generate will be discrete raster. So we are going to style it based on the need for styling for this discrete raster, so that we are going to use on the color rendering the plated single values. As you can see, this is a single band gray, so I'm going to use plated these unique values. Then I can click on the classify button. Then as you can see, the classification is already here. For the next thing will be to each unique value we are going to assign a raster unique random color. So I'm going to right click on the random colors, and I will select blues here, because this one are rivers. Now the stellar layer, if you visualize it from the map on the canvas, as you can see, you can clearly see that the streams with a higher order has blue color with somehow higher magnification. So we can see the rivers are here with the highest order, and the smallest order. The rivers with the smallest order will be the tributaries, and with the highest order will be the highest one. So the next thing will be to calibrate the stellar threshold to determine streams. As you can see from the map, the visualization, you can clearly see that there is a stream network around here, because the blue dots are somehow higher. If I zoom in and come to the detail, I can clearly see the streams and the tributaries on a better magnification, on a better resolution. So the next thing to do will be calibrating the stellar threshold to determine the streams with the highest orders and the smaller orders. So we are going to create a Boolean layer from this discrete layer. As we discussed in the class, we have mentioned that the discrete ones are the layers, those have finite number of values, and the Boolean layer can have only two values, whether true or false, or 0 or 1 values. So we are going to create a Boolean map and calibrate the stellar threshold to determine the streams. How we are going to do that? We are going to use raster calculator. Now let's do that. Now we are going to create a Boolean layer for stellar order larger than or equal to a threshold value, a certain threshold value. So each Boolean layer will be compared with a reference layer. Here we will compare the stellar order with the rivers on OpenStreetMap. For the areas where there is lack of data in OpenStreetMap, you can use Google Satellite. Both OpenStreetMap and Google Satellite layers can be found on the Quick Map Service plugin. So I'm going to navigate to Web, then Quick Map Service, then I'm going to OSM, OpenStreetMap in essence, then I'm going to choose OpenStreetMap Standard. Then I'll see whether my layer is on the OpenStreetMap. As you can see, my layer is on the OpenStreetMap. As you can see, there are a lot of streams around the project area. For example, I can style the boundary layer. I can make a simple fill to be a transparent fill. Then I can call it apply. And I can uncheck the structural order and fill them and check the boundary layer. As you can see, there are certain streams over here. And as you can see, this one is, I think, the bigger Angereb river, which is a tributary of Tekeze, which is also a tributary of the Nile River. So there are also certain streams here that will join the Tekeze River. That's one of the main tributary of the Tekeze River. So we are going to check here the structural order with the different streams that are found, the local streams in the area, and we have to compare it with the ones in the OpenStreetMap. And in my case, I have decided that I'm going to use a threshold of 8. That means I'm going to consider streams that has a structural order that has more than 8 value, so that I'm not going to consider each and every streams on this area. I will only consider the main ones in this specific boundary of project area. Then I'm going to navigate to raster, then raster calculator. It will show me the raster bands or the raster layers, which are the hillshade, the reproject, the creep mask, and the structural order. I will check the structural order here, and I will use the expression here. If I double click this one, the structural order at 1 will be with display on the raster calculator expression dialog box automatically. Then I will make my values greater than or equal to 8. Then I have to save also the output layer here in the folder where I am working currently. This one is Ethiopia modified, and the file type will be, it doesn't matter, to be geotiff. Then I can say structural 8. That will show me what kind of threshold that I'm going to use. Then after running this, I will put it here. I will put everything to default, the layer extent, x minimum, x maximum, y minimum, and y maximum, and the output coordinate system is set to the project's coordinate reference system. Then I will run it and create a Boolean map. Then it's calculating, that you can see the raster calculator has finished, and you can see that there is a structural 8 layer here. Then I'm going to do layer styling also to make it's a good practice also to style this layer too. Then I will select this one and I will click on the layer styling. Make sure that on this selection box the structural 8 is selected. Then I will choose this plated unique values. Then I can say classify. As you can see, because it is a Boolean raster, you can have only 2 values, 0 and 1. In my case, I will have no streams value and streams value. Then this layer is a boolean, and therefore it only has pixels with values 0 and 1. For our calibration, it is important to make zeros transparent and ones blue, so we can compare the raster with streams on the OpenStreetMap. So that I'm going to make the streams a blue color, and I'm going to make the ones with no streams with a white color or a transparent one. Then I will choose, before doing anything, I will change it. I will change the color of one to dark blue because it will resemble the stream. So I'm going to select a dark blue here. Dark blue will be, I will select from the single layers, the single colors here. This one is a dark blue, and I will set apply. And when I go back, because you can see there is 0 and 1, I will change the labels here. I will say this one, no streams, no stream, and the one will be stream. Don't bother about the color of no stream value because we are going to make it transparent. Then the next one will be clicking on the color one, making the arrows transparent. Then I will go to the transparency tab. This one is a transparency tab, and I will add 0 as additional, no data. And as I mentioned, I already did the live update, so I don't need to click apply every time. So it's already added. Then I will recheck it whether I added 0 or not. Then the next thing will be checking these streams with the actual open map value, OpenStreetMap. Then see we are doing a good work or not. And if I zoom in and check in, as you can see, most of the streams are aligned. For example, if you see this one, the alignment is almost the same. With an OpenStreetMap, as you can see, the stellar order that I generated is following the actual river network. So we are doing a good job here. Then the next thing will be calculating the channel network flow direction and the basins. So we are going to use a Saga algorithm here. I will type channels, and I will select channel network and drainage basins as a basic algorithm to develop this channel network and drainage basins on this specific project area. So I will double click here, and okay, we selected the channel network and drainage basins. We have to select on the elevation dialog the field name, and the threshold for stellar order should be 8, and the flow direction we have to save it as flow direction with SR format. You have to navigate through this and save to file, and you have to save it as this flow direction to resemble it is going to have this flow direction. Then similarly, I will also set the other options here to generate these channels and also to generate these drainage basins. This process is going to take somehow a longer time, so I'm going to run it and expect that there will be 3 layers that will be generated. We are going to have channels, that has a shapefile or a vector data type, and basins, which is also a vector data type. And we are going to have also flow direction with a raster data type. So we are going to expect on the output 3 generated layers. And finally, after the algorithm finished, we are going to style each layer and proceed to the last step, that means specifying the outlet of the basin. So I will click right here and wait for the algorithm to finish. Okay, now the algorithm has finished as we have expected. As you can see here, there are 3 additional layers: the flow direction, the drainage basin, and the channels. So we are going to style these layers. We have to zoom to layer with one of the layers that are generated. For now, I'm going to select the channel 1. Then I'm going to select the styling panel. Then I will select here on the single symbol. I will select here the graduated one. Then I will set the parameters. I will set the column to order. Then I will select the method to size. Then it will be in millimeter. And the precision to 0. Precision should be 0, and the size should start from 0.3 up to 1.0, and the unit should be millimeters. Then the mode of classification, keeping the default mode of classification as equal interval with the same number of order classes that exist in your class. Then we can review the attribute table if we need to be. In this example, we are going to set the classes to 3. We are going to set it to 3. And we can click classify, and as you see, it's already classified. Then we are going to click on the change button. Then we are going to change the color to RGB of R value of 15. RGB means the red, green, and blue values. Those are the dominant ones who can change the overall visualization of the color. Then 1566, and the blue one should be 220. Then I will come back here. I will go back, and as you can see it looks like a stream now. The ones with the smaller straddle order, and the ones with the medium straddle order, and the ones with the higher straddle order are here. And now the next thing will be, if I want to change these values to integer, I can also change these values. You can also change it with this one, 1 to 2, and values you can change it. The straddle your map now should be, your map will have a better visualization, and showing the streams identified as higher straddle order are the main channels. That means these ones, the ones with the higher ones, and the smaller orders will be the streams and tributaries. That means the other two. And I will say okay. If I want to edit the legend value, it's better to edit the legend value. The legend value, I will edit it. I will set this one with standard order 1. This one, it's better to do it just like this for a better visualization. 2, and I call it 3. Now this one is better. This one has a better visualization now. Now we are going to style also the, I'm going to select apply, and we are going to style the flow direction layer and see the changes. But before going to style the flow direction layer, it's better to see how we are doing in terms of streams. As you can see, these ones are the streams with a high order and with a smaller order based on the standard order that we have defined initially. Then I can also have the field them and see the streams clearly. As you can see, these are the streams. If I check in the drainage basins, you can also see the basic drainage basins. Now we are going to style the flow direction layer. Here we have the flow direction here. I will select it and select the style. Using this layer styling palette, setting the layer to flow direction, we have to check in the flow direction layer is selected. Then I'm going to select the color rendering to plated unique values. Then after selecting selecting these plated unique values, I will select classify, and I will have, as you can see, 8 values, or we used we used 8 directions: 0, 1, 2, 3, 4, 5, 6, 7, and 255. 255 is resembling or representing the flat areas, so we don't need the flat areas here. We have to remove it from classification. We will click, we'll select the 255 and select the -1. And on the color ramp menu, we have to select here the spectral one as spectral color ramp as a beginning point, and selecting the color ramp here, a new window will pop up, a window just like this. Then we will, this represents, here you can edit the color stops for the ramp. The idea is that the far left and the right sides will represent the northern flows, and he will set both of those stops to the same blue color. You will then set the center stop to a bright yellow for southern flows. The stop in the middle on the right will be the western flows, and the stop in the middle to the left will be the eastern flows. Now these are the flow directions. The first one represents the northern direction. The last one also represents the northern direction. This one is the eastern flow, and this one the southern flow, and this one the western flow. Now I will click the drop down menu for color ramp 1, this one, and I will select the peak color, and my mouse pointer will change to an option to pick this color. Then I will select color 2 and click on the center stop that will represent the southern flows. As I told you, this one is the northern one, this one is the eastern one, and I will select the southern one, and we will assign it to a bright yellow by entering RGB values to 55, to 55 and 0. The RGB values will be, I will make the window a little bit larger. R will be to 55 and G will be to 55, and I will make this one 0. And for eastern stop, this one is eastern stop. I will select the eastern stop here. I will make the RGB value 0 to 55 and 0. R will be 0, G will be to 55, and this will be 0. Then for the western stop, we will use a magenta color. For the western stop means this one. The magenta color will have the RGB value of, this one is a western one, it's already selected. This one is, R will be 240, and G will be 16, and B will be 170. Then I will select OK to accept the current color ramp. Then I will click on the plus button to add a new classification scheme. I will select plus. There will be an additional H value. Then there will be a new value to classification for the value type 255. Here I will type 255. This represents the flat areas you initially removed before creating the circular color ramp, and I will select the color patch and select white for that, and I will go back to the color selection. As you can see, this one is the edge or the flat area is represented with a white color. Then to review this flow direction data, you will now give it a blending mode of multiply. Now we are going to give this one a multiply, and the other one will be, we can turn on the hillshed layer. As you can see, everything is finished now, and we can go out. As you can see, the flow direction is now better, it has a better visualization. Rather than using the field DEM, I will turn on the hillshed, and I will make it below the flow direction. Then as you can see the flow direction clearly here. The gorges can be visualized here clearly, and as the point, just we should have now the channels, the flow direction, and the hillshed layers turned on. The channels is here, the hillshed is here. I will turn off the Stellar 8, and the OpenStreetMap standard one will be turned off also. Now I only have the channels, the hillshed and the flow direction. As you can see, you can clearly see the direction of flows here. I can see the mountains and the gorge areas clearly. Then you can zoom into some of the more mountainous terrain in the south of the study area where there are also channels present. You can inspect the data here where the flow is where the flow is locating. You can see there are hills, and also there are gorges, how the channels are going or following the direction of flow. That's representing the flow direction. Then we can see that now the southern areas, for example, these areas facing the slopes being represented by warmer colors, and the northern by color. Eastern flows will be greener and western flows will be more purple. If I put the channels above every layer here, I can see clearly the direction of flows where it is following the gorges here. Now the next step will be defining the outlet point. In this condition, we are going to need the drainage basins specifically, so that we will see how the specific streams are draining. For example, if I put next to the channels, I can see that the drainage basins are already demarcated, so that the channels are following a specific route. For example, you can see this basin here, it has tributaries and mainstream, and you can also locate outlet points at the end of each specific basin. So we are going to use that. Now we are going to define an outlet of this drainage area. As you see, the drainage basin is already specified. We said that it is an extent of an area of land where the surface water from rain or melting snow or ice converges to a single point at the lowest elevation. This single point should be an outlet. For example, for this drainage basin, the one which I am hovering the pointer, the outlet area should be around here. As you can see, it follows the bigger river here, so we have to select an outlet area around this point. So we are going to put on the vector. By now we should have the drainage basins turned on, the channels, and also the standard map. As you can see, the open street map will be used to identify the exact stream point. On this condition, we are going to select an outlet point that is on the stream network. You have to make sure that you clicked on a point that is exactly on the stream point. From the open standard map, as you can see, we are delineating a catchment that is mainly the main river is called Angereb. This one is a tributary of the Tekeze-Angereb, which later joins the Nile River. So we are going to turn on the coordinate capture. For example, I can vector, then go and see coordinate capture, and I can say start capturing. Then I will zoom in and select specifically the stream here, not another point on the map, so it's better to select the stream. So my point is on the stream, and as you can see, you can copy to clipboard and paste it somewhere if you want to set the drainage point or the outlet point that you have selected. I am opening a Word document, then I can say paste. As you can see, it has I have everything here, so I can do whatever operation that I'm going to do on the next step. So I already specified the outlet point on this project. Then the next thing will be delineating the catchment. That means specifically extracting the catchment that is I am interested on, or the project area is located. Now the next step will be delineating a catchment. We are going to calculate the upstream area, that means a catchment that produces a discharge at this specific outlet point. So we are going to use the upslope algorithm. The upslope algorithm, which means the terrain analysis hydrology. I will double click on the upslope area. On the target area, it is optional. We have to leave it as a default. target X coordinate, I have to copy from here to here and say copy, and the target X coordinate will be, I will paste here, and the target Y coordinate will be this one. I will copy and paste it here, and the elevation I have to select field name here, and the sync route, it's also optional, you can leave it as simple, and the method will be deterministic aid. The convergence, I will leave it to 1.1, the default value, and I will save the file here, and I will call it the catchment, because I am specifying the catchment area. Okay, then I will click run. And I will wait until the algorithm finished calculating. It will take somehow a longer time. Now we have finished calculating the upslope area or the catchment. The next thing will be polygonizing the result. So first let's visualize the result. That means I have to put upslope area here, and as you can see, the result here is a raster layer, which is upslope area here, which has certain watershed, which is a raster value. Then I have to polygonize it. I have to navigate through raster and conversion, then polygonize, and I will select the appropriate layer here. In my case, I will select this upslope area, and the band number should be band 1, and I will call the vectorized layer as, it will be a shape file. I will call it Angereb catchment. Then I will save it. Then I will run the algorithm. Then the algorithm has finished calculating. I will say close, and I will only have the vectorized one. I will also uncheck this one, and as you can see, I have the vectorized output. As you can see, the catchment area is already delineated, but there is also an outer area. So to check the attributes, I have to open the attribute table and check whether which parts have to be removed from this catchment. For example, when I'm selecting this one I have to see the changes. I will open editing mode. I will open it and see the area each one representing. For example, this one represents the outer area, and for example, this one represents inside area. In my case, I only need this, the fourth one, so I have to delete the other values. For example, this one needs to be deleted. I have to click delete, and as you can see, the original catchment area is left here. As if you want, you can also delete these values. Otherwise, you can also keep it. We will see whether it's going to create a change on the actual catchment or not. I will delete it. As you can see, there is no change. I will also delete this one. Now the only thing left is the one with 100 value. So I will save my results, and close the attribute table. I have to also uncheck the toggle editing, and I have to uncheck the drainage basins. As you can see, the drainage basin for angular catchment is already in the vector form, or it is delineated. If I put on the channels on the top, as you can see, the channel is already here. So the next thing to do will be clipping. So clipping the area, or the area that is, by using this vectorized layer, we are going to clip the streams, or these channels, so that we will have only the streams that are inside the angular catchment. So we are going to do this clipping process. We have to also clip the DEM also, the field DEM with this extent, and finally we are going to have the final catchment that has the elevation and also the channels at the same time. So we are going to do that. You know how to do these processes. At this point, we are going to have only the 4 layers. That means first one we will have the field DEM, the channels, and the vectorized, and also the OSM standard. So I'm going to remove the other layers. I have to press Shift and the down arrow, select everything, and I will remove it. I will say OK, and I will say clipped. I have to remove it. Okay, and then standard border, I have to remove it also. Okay. Then the next thing will be clipping using the extend area. You know how to clip. Vector, geoprocessing tools, and clip. Then it is already only selected. The input layer should be the channels, and the other should be the overlay layer will be the vectorized or the angular catchment, and the new one will be, I have to say, save it to file, and the new one will be angular streams. Okay, then I will say OK, then I will run it. Then the algorithm has finished clipping the streams inside the angular catchment. Now I also don't need the channels, so I will remove this one. I already removed the channels layer. Now I already have the clipped one, so I have to change it to a blue color because it is representing a stream. So we better have a better layer, a better representation, a better color representation. So sorry. On the simple line here, I will change the color to blue one. This one is better, and I will say apply, and I will say I will close it. Now you can look that it has a better visualization. Now we have to extract also the field DEM with the extent of angular catchment. So we are going to use raster, then extraction. You have to say clip raster by mask, like we did for the subsetting of DEMs. And the input layer should be the field DEM. Then the mask layer should be this vectorized format, and the source and the target will be, everything will be a default value. I will put the no data value to output lands. I will, that is, we have to give here, the only difference is that we have to give no data value that is out of range of elevations. We can use -9999. Then we have to say the clipped mask should be saved to a layer which has a TIFF file type. I'm going to say Angereb elevation, because it's going to represent the elevation of the area. So I'm going to run it. It's saying that there is a warning, there is a ring self-intersection or near point, which is on the vector format. Sometimes this kind of errors can happen, so we are going to fix this error. Before proceeding to that, we have to fix the geometry of this this vectorized or angular catchment or vectorized layer in our case. So I have to check whether, yeah, I have to check here, fix geometries. I will click in here, fix geometries. It already have this one. I will select save to file, then I will say Angereb catchment fixed. Okay, so this one is Angereb catchment fixed, and I will say save and I'll run it. Now we already have a fixed geometry here. Now I don't need this vectorized layer. I will remove it. Then I will say save. Then I will come to the extraction process. Flip my mask layer. The input will be a field DEM. Then I will set everything to default, and I will set no data value to -9999. Then I have to say save to file. Then I call it Angereb elevation. Okay, and I'll save it. Then I'll say run. Now I already have the clipped layer, so that I will save this one, and I don't need the field DEM anymore. Yes, I will say okay. Now I have the one, so I have to make sure that this will be styled in the proper format. I will select single point pseudo color, and I will select here the create new ramp. I will select the catalog city CPT city, and I will select here the topography, then the elevation. Then I will say okay. Then I will come to the blending mode. I will make it multiply, and I will say apply, and I will go out. Now I can clearly have this value, this Angereb catchment. Then the next thing to do will be styling the resulting catchment area. Then by setting the layer to this fixed geometry and select the styling, I am going to have the simple fill, changing the single symbol render to inverted polygons. Then the next thing will be this render, this single polygon, the inverted polygon render. This renders the data as an inverse from its geometry. That means the other part from the outside the geometry will be rendered. Then this creates a mask around the rule of the angle of catchment, the angle of catchment valley. This way it will create a render. Then we will select the simple fill component. Then we will change the symbol layer, the symbol layer type here to sharp burst fill. There is sharp burst fill, as you can see. Then in the gradient of colors, in the gradient color of section, the default will be 2 colors. Then we will change the first layer to RGB values. We will have RGB values of 135 for each. 135. G will be also 135 and B also 135. Okay. Then the next thing will be in, I will go back to here. Then in the shading style, in the shading style section, we are going to click the set distance option. We are going to make the distance to 4. I'm going to make it 4. Then the other thing will be under the layer rendering. We have a layer rendering here. We have to expand it. There is a layer rendering. There is opacity. Opacity should be 65%. Should be 65%. This will make the open standard map visible, as you see from the QGIS canvas. Then finally, at the top of the layer setting panel, we are going to go back to the top of the layer setting panel. We will select the sharp burst fill component. Then we will add another one here. Then we will change this new simple fill render to a symbol layer. We are going to change it to from a simple fill render from a simple Now we are going to change the symbol layer type to outline simple line, this one. Then the color should be the default black, and stroke width should be higher than it should be 0.46, and this will give us nearly a good visualization for the Angereb watershed. I will say apply, and I will make it just like this. If you want a better visualization, you can say zoom to there, and you can see the catchment delineated just like this. You can see the channels over here. You can see the elevations here, the elevations, the maximum and the minimum. We can make it continuous if you want. It starts from 700 to 3039. You can navigate to here, properties, rather than, I think it is continuous, but we can style it later. I will also make another video for final map making and styling. This is all about catchment delineation. Then there are boundary conditions that you should consider when you are doing this catchment or stream delineation. This generic workflow only works on the surface that has ups and downs of the elevation areas, the mountains and the gorges. It doesn't work when it is applied to flat areas or human controlled environments. You should consider these boundary conditions before doing this catchment or stream flow delineations. Then after doing these catchment delineations, you can use it as an input for modeling. For what kind of modeling? You can use it for rainfall runoff modeling or hydrological modeling or hydrologic modeling. Additionally, you can use it for agricultural management or infrastructure. And there may be various applications of stream or catchment delineation. You can Google and see what are the basic applications of this catchment delineation. And I thank you for your attention. I hope you will learn a lot from this video, and you can do catchment delineation for any stream that is on your project area. And thank you for watching again.